Alright, today we're continuing with combined inequalities, and let's explain what I mean by that. What we're going to have to first know is that the words or will mean a union, and the word and will mean an intersection. So if I should write, let's focus on the or first. So if I wrote a question such as this: x is greater than 3, or x is less than or equal to -1. In terms of set notation, what I'm really saying is that I have the set of x's such that x is greater than 3 union the set of x's such that x is less than or equal to -1. Alright, so either way that we see this question, we should understand that whenever I see the word or, it means a union, or whenever I have the union, the equivalent word or verbal statement will be or. Alright, what do I mean by this? So let's take each of these inequalities and graph. So let's look at the first one here. Well, we'll just draw a couple number lines for each and see what they look like individually. So the first one, x is greater than 3. The second one, x is less than or equal to -1. And then the third one will be that combined or. Alright, so if we look at the first inequality, what I'm going to do is just graph them, and I'm going to actually even match them up a bit. So here was 3, -1 would have been somewhere down here, and so on. Okay, so, but definitely I will put in the numbers as I need them on the various lines, but I'll just center all the zeros and the points. Alright, if I am going to graph my first inequality, x is greater than 3, then I would have an open circle, and we would be looking at everything to the right of 3, correct? Alright, let's go on to this. Nothing great yet. Let's look at the second inequality, x is less than or equal to -1. Again, we find our boundary value, -1. We shade it in because of the equal sign present, and we're going to shade everything to the left of -1. Alright, let's look at this in a combined mode now. Since I'm going to be looking at what's happening at -1 or 3, let's just look at all 3 lines together. So if I call this region 1, region 2, region 3, then the boundaries will actually break up the number lines into these 3 regions as indicated. And if let's put in the numerical values here, so we have -1 and 3 for those boundary positions. What happens when we're taking a union? If you remember from your set theory, a union is just a joining of the 2 sets without repeating numbers, etc. So the idea here is I'm going to ask the question, in region 1, is there anything shaded? And if there is, then in my final line, in my solution set for the or statement, I will have to include it on my number line. So if I look, then definitely this region is there. Okay. Let's ask about the boundary value. Is it present? And the answer is yes, it was present in number 2, so it would be present here, right? So we have that. Oops, I guess black is the color formed when we have green and red. Okay. All right, so let's go to the next region, middle region. Nothing is shaded in there, so there'll be nothing being contributed to our final answer, final number line. In the third region, we have line 1 was shaded. The boundary value 3 was not included, so that would be an open circle. It wouldn't be included in the final answer, but everything to the right of 3 would be. So in our final, or answer, or solution is, so this is our solution graphically. And if we were to write this in set builder notation, then because of the 2 portions that we have, we would represent it just as we would reading off from the graph, the set of x's such that x is less than, or set of x's such that x is less than or equal to -1, or x is greater than 3. All right. So reading from left to right, you put them in the same order. You also ask the question, you know, which region do you have in the final solution? And this is what we have shown. We had two places that you could be, either what I'm calling region 1 or region 3, which have indicated their names using my set builder notation. Sometimes when we have these like there's no end to our solution, we call these sets, right? So there's no end in either place. So we sometimes will say that this is an unbounded line or an unbounded solution. Okay. All right, but don't worry too much about those names. Just try to see if you understand. The word or means a union. It is almost as if you were doing this when you had the roster method. You had listed out the elements one by one. It's just that now it's a continuous or found on a number line, so quite a lot of values there. All right, let's try this again, and let's look at a second one. Right, so see if we get the idea. So we're not really complicating things, we're just taking some simple inequalities. X is greater than or equal to 2, or x is greater than 0. And we want to find out, is this like what we had above? Will this give us a number line with 2 regions, since there are 2 sets there, if you look at them that way, or what's going to happen? So again, let's start off by drawing our various number lines. You'll notice I'm actually just putting the inequality here rather than just saying the letter X. It's a little deviation from what I had said to you in a previous lecture. But I think, again, it's self-explanatory. We need to identify what's going on. All right, so let's put in, I like to indicate zeros throughout, although it will be a boundary value this time. Okay, so again, let's find this. X is greater than or equal to +2. So closed circle here. And then everything to the right of this will be shaded. Okay. All right. Next one, we have x is greater than 0. So an open circle at 0. And also everything to the right will be shaded. Okay. So if we now look at our number lines and sort of divide them in regions, we're seeing again 3 regions. That's again because we have just 2 inequalities. So the 2 boundaries have separated our number line into 3 regions. Alright, so recall that we are using the OR. The OR is a union. You're joining these sets together. So if there will be a solution or something will be present if it is in one or both sets. So if we look, region 1 has nothing, so there will be nothing in the first region. Region 2, definitely we will have something going on. I'll deal with the regions first. Region 3 would have something. Let's look at the boundaries. When we look at the first boundary at x equal to 0, will that be an open or a closed circle? Well, it has to be an open circle because it was not included in either sets. So remember, in the union, if it is not there, you couldn't just miraculously put it in. So we'll have an open circle for x equals 0. Alright, in the second boundary value, x equal to 2, it is distinctly shaded in the first set here, and it's implied that it is present in the second set. So either way, we know that in the final solution it will be present, so I'll just close that gap. So in this case, unlike the previous one, right, let's go back. The previous one, we had an OR statement and we ended up with 2 regions indicated, as indicated. Now we still have an OR statement, but this time when we look at this all together, we see, or we can write that our solution set is a set of x's such that x is greater than 0. We end up with one region that is shaded. Again, we call this an unbounded set. Alright. Let's go on to next question. Alright, question 3. X is greater than -3 or x is less than 1. Okay, so go ahead, proceed, and then we will compare our answers in a bit. Right. Again, if you're watching this on tape, please remember once I put up the question to pause. I do that in the classroom, but in order to conserve or cut down the length of the viewing tape, we have edited out or paused the lectures on this time. Okay, so again, I like to put in my zeros just to indicate when we have what's positive, what's negative. Okay, going back, -1, -2, -3. And I'll just put those in. We also have 1. I'll put that in. Alright. So x is greater than -3. Open circle. Shade everything to the right of that in our first number line. Second number line, we have x is less than 1. Open circle again at 1. And shading everything to the left of 1. Did I say left or right of 3? Alright. As indicated, I've done it correctly, but I may have said the wrong thing. Let's see. Alright, so now let us look at our regions and determine which region will I shade in my final solution. Oops, there we go. Sorry about that. region 1, region 2, region 3. Alright, so in region 1 we have a portion that is shaded before -3. We see also in region 2 this is shaded. So finding some of the places that we will shade, it's not a big deal, it's not very difficult. It's usually around the boundary that you might have to do some bit of thinking. Alright, so when we're at -3, should I include that or not? Well, if you look here, it is included, so I will put that in my final solution. Going to the number 1, no, it's not included here, but yes, it's included in the first set, the first line. So in my final solution, it is included. So what do we have here? Well, this is a bit interesting because now I've basically shaded the entire line. So my solution set is really, you have two ways of writing this. You can write this as a set of x's such that x is a member of R, or simply the solution set is the set of real numbers. Okay. Since we were dropping the notation of putting x is a member of R, it's quite fine for you to choose the latter. Alright, so the point about these questions is that it does require you to think or look at the individual components that you're using and then determine how do you put them together with the union. And all it is just reminding yourself what does it mean when we say we're taking a union. Right? So here are 3 different examples that I've given you, and depending on the numbers chosen, we have seen where we could have 2 distinct parts of your number line being shaded, 1 part, and I don't know if you see this, but here what happens is one number line, in number 2 here, what happens is that the set of x's such that x is greater than x is greater than 2 is actually a subset. Do you remember this symbol? It's a subset of the second set, the set of x's such that x is greater than 0. But as I said, everything will fall into place if you just look at the components and then remembering what a union does as this joining together of 2 sets, then you shouldn't go wrong. Alright, let's move on to the AND. And as I mentioned before, the AND statement really meant your intersection. So let's similarly do 3 questions where we look at the intersections. Okay, so question 4. If we have x is greater than or equal to -1 and x is greater than 2. Start out as usual with your 3 number lines. Watch the conjunction if you wish. The word is AND. Alright, so x is greater than or equal to -1. X is greater than 2. Let's put in our 0 mark. -1. I'll put that in all of them since it's a boundary. Alright, so let's see what do I have in on the first line. First line I have a closed circle at -1, and then we would shade everything to the right to indicate x is greater than or equal to -1. Next I go to the second line, x is greater than 2, so it's an open circle there. And again, I shade everything to the right, but 2 is not included. And as I did above, let's look at these region by region. So if I do that, what I end up with is these three regions, as we had earlier. And we can ask the question, what does an intersection mean? An intersection means that it must be common to both sets. The only place that we have things being common is in region 3. Region 1 had nothing. Region 2, although it's present in line 1, it's not in line 2, so it would not be in the intersection. So definitely we have region 3 because it's present. The elements of one set is present in the second set in this region. We now have to think about what happens at the boundary 2. So 2 is not included in the second set. So if it's not included in one of the sets, it can't be in the intersection. And so we would end up with an open circle at 2. So my final solution for this AND statement is as seen on the graph, and it is a set of x's such that x is greater than 2. Again, we're seeing that one set, the second set, is a subset. So if I had written this here, then this would be a subset of the first. All right. Okay. Let's go again. All right. Number 5. X is less than or equal to -1. And x is greater than 3. X is less than or equal to -1, x is greater than 3, and we have the AND statement. All right, let's put in our zeros. And -1 and 3, and we know in the final solution we typically will need to look at these boundaries, so let's insert them. All right, going at -1, this will be included based on the inequality that's present, and we will shade everything to the left of -1. Going through, second inequality, open circle at 3, shading everything to the right, and then let's look at combining them, combining these two sets to get the combined inequality. So again, let's look at region 1, 2, and 3. And to have an intersection, we must have the elements common to both sets. And there is no such thing. Nothing, nowhere do we have any region that has anything in common. So we end up with a blank line, and this, so our solution set is equal to the empty set. Recall that when we even had the Venn diagram, for those of you who are listening strictly on tape, I may have edited a part of this prematurely, so I didn't give you the name of it on the previous or early lessons, lesson 1. When we had two sets and in our Venn diagram, and we had them as shown, we would say A intersected B was equal to the empty set. They had nothing in common. And there is a word for this. We'd say that sets A, right, sets A and B are disjoint. So in essence, what we have here is a similar picture. There's nothing in common between the two lines or two inequalities that we had, and hence we have a resulting solution of the empty set. Okay. Let's continue some more. X is greater than or equal to -3. Oh, right. One of the students just asked and said, you're seeing that you can get every possibility with these combined inequalities. If we go back to our statement, what you ended up, there are sometimes when you were looking back at your Venn diagrams or so on, or elements, and sometimes when you combine them, when you took the union, you ended up with the entire universal set. So here we saw back in number 3 the case where you took the two sets and you ended up with a set of everything, in our case meaning the real numbers, while as we went down further, when we go down here to this number 5, we've ended up with taking the intersection and gotten the other extreme, the trivial example or trivial set of the empty set. Okay, so every possibility could happen. Alright, x is greater than or equal to 3 and x is less than 1. Alright, if you think you knew everything up to this point, guess what? Of course there would be something new. So, get a little curvy there. X is less than 1, and we're looking at the AND statement. Let's put in our zeros. One, and put both in down at the bottom. Alright, and as usual, complete this to be greater than or equal to -3. It will be a closed circle, and we would shade everything to the right of 3 also, -3, sorry. And going on to the next one, open circle at 1, shade everything to the left of 1, and as usual we're going to look at these as regions, and in those regions let's see what we have. Region 1, 2 and 3. Okay, we are looking at the intersection, so already you should now see only in the second region, region 2, will I have anything. I may have, may have done too much, got too close to that boundary with my color in there. So let's go again. Oops. Okay, so let me stop there. Alright, so at the boundary, let's deal with -3 first. Will it be included in the final or in the AND statement? And the answer is yes, it is included. It's present here and implied just by the continuity of that shaded region that -3 is included. So it's included it's present in both sets, so by the definition of intersection it will be included in the final. Alright, if we now look at 1, yes, it's in the first set, but no, it's not in the second set. So in the final solution it will be an open circle, 1 is not included. Right, and so this is a graph that represents our solution. Now, as you can see, this represents on the graph one region, and we want to be able to, as we're looking at things, if we, let's go back a bit all the way up to earlier things. You will notice that if I am dealing with two parts, two portions, then I had that in my set builder notation. If I had one region, then it was one set in my set builder notation, and so on. Well, those were extreme cases, the entire real number. But in number 4 here, one portion, one set. So we would like, as we look at number 6, we would like to write this, since it represents one region, as one inequality. And this inequality is sometimes, or this region is sometimes called a bounded region. That is, it has an end, or it has ends. And as we can see here, it's what we call half open or half closed, because one end is open. But it's bounded versus, say, the portions, the parts that I had. This up here was unbounded, right, but closed on one end. But when we have a bounded region, we're going to do different examples to look and see what can happen. All right, now in naming what's going on here, so let's even describe this verbally. I could say that I am between -3 and 1, and -3 is included in my solution. So how can I write this? So using the letter X, what I can say is X is between 1 and -3, or -3 and 1, and -3 is included. All right, so we can look at the order of the numbers on your number line and write them this way. I'll soon explain another way of looking at it. So this would be written in set builder notation, a set of x's such that -3 is less than or equal to x is less than 1. Formally, when we say, so maybe I should indicate that this is an informal way of speaking. The formal way of saying this is exactly how the question is written. Let me just break it up a bit. What we have here is -3 is less than x, and at the same time x is less than 1. Now recall that I told you whenever we're dealing with inequalities, we don't like to put this, in English we call it the passive way. -3 is less than or equal to x. We'd rather have what we call an active voice and describe what is going on with x. So in order to do that, I'm going to use my exchange left and right hand sides as I had done earlier. Recall that this switches the sense of the inequality, but this is nothing more than what you started with. So it turns out that what you started with these two inequalities, can be written in a more compact form, which is what we have here in our set builder notation. All right? So this is the preferred form because it represents one region. Okay. Let's do a bit more practice, and I'll come back to looking at graphing these parts with the AND statement, and even looking at the combined inequality and working with them. Right? So let's go back and look at maybe a more typical question. So no, you're not going to be given where they're already solved. They're just some little inequalities and you're joining them by the and or. We really want you to work. So instead, suppose we have 2t plus 7 is greater than or equal to 13, or 5t minus 4 is less than 6. So the first thing that you have to do is simplify each inequality, and then we'll be able to put them together on the number lines and look at what the or union is doing. So going through and solving, I'm transposing 2t is greater than or equal to 6. Dividing throughout by 2, it's a positive number, so I don't have to worry about anything. And so I finished the first one. Second one, 5t is less than 6 plus 4. 5t is less than 10. Dividing both sides by 5. So these are our inequalities, and essentially this is now the starting place that I have, or what that we looked at before. So as usual, let's draw the 3 number lines. Oops. First one will represent t is greater than 3, t is less than 2, and the last one will be our or statement. Okay, everything is on the right side of 0. So let's put those numbers in. Okay. If t is greater than or equal to 3, close circle. You're getting the hang of this by now. And similarly, second one, open circle. For the strict inequality, it's just a less than 2. So we would have everything to the left of 2. Alright, putting them together. Recall what we did. Let's look at these as regions. And if we do, when we're putting the union together, it must be in the union, you must be in one set or the other or both. And so we end up with that region 1, region 3, and if we go back to the boundaries, 2 will not be included, but 3 will be included. So overall, for this final thing, my solution would be the set of x's. Remember to write it in the order that you see. Set of x's, x, I got caught. I'm the one going in automatic mode. T. T is less than 2, or t is greater than or equal to 3. And that's my solution. Okay? Alright. So most questions that we will be giving you, you will have to do a bit of work first, computation, and simplifying your inequality. Get to the simplified version, put that version on a number line, and then use it further with your and then or. I think that was number 7. Okay. Alright, let's look at the same thing would apply to an and question, but what I want to do is I want to look a little bit more closely at what we call at the bounded inequalities. Right. And first of all, let me just do a couple things, and let's ensure that we can name them. So let's call these A and this value B. On our number line we'll do x's. Alright, let's look at several combinations. Suppose we had both open, both closed. One open, one closed, one open, one closed. Alright, and there. Okay, let's look at the naming of these. Alright, the naming, again we want to use the set builder notation since this is one region, in each case one bounded region. We will say that this is a set of x's such that A is less than x is less than b. This is known as an open interval. Okay, both ends are open. On the other hand, same boundaries, but because of the closed or closed circles on both ends, notice the inequalities have changed. So this is a closed interval. If we look at the third ones, at A it's open, but at B it's closed, and vice versa for the fourth one. So we have a less than or equal to sign and a less than sign. Both of these are called half open. I guess, again a student is asking, could it be called half closed? Sure. But the typical thing is half open, and these are the different things that we could have in those bounded type of inequalities. And again, remember that each of these, whatever I have, whatever the form, this really is the same as saying x is greater than A and x is less than B. You are looking at that and that part. So it's taking pieces. Alright, let's look at working with these bounded inequalities, however. So I think we are now on number 8. Negative 7, 2x plus 3 less than or equal to 5. And we're going to say x is a member of the, we've been doing this anyway. Alright, so we want to solve and graph. And yes, set builder notation, of course. Okay. So what would we do? Just like any, rather than taking this apart, we'd only take them apart if it's very complicated, but right now it's not that bad. And essentially we're going to treat it just like our inequality. Anything I do to one part of it, I'm going to do to the other. So normally we want to isolate the variable, so I'm going to subtract 3 from the middle, but if I do that, I have to do that to both ends. And what's the result? I end up with negative 10, 2x, and 2. Okay. So the first step was subtract 3. The next step that I want to do is to divide by 2. And the aim of that is so that I can isolate x. That is, get x by itself in the middle, which is what we were doing with all of these bounded inequalities that I had written out symbolically above. Right? So what do we do? Let's write that again. No big deal, I'm dividing by 2. If I'm dividing by 2, nothing happens to these inequality. It's a positive number, so we end up just with negative 5 is less than or equal to x, which is less than or equal to 1. If I should graph this on a number line, the key points are the boundaries, which are, say, negative 5 would be somewhere there, 0 would be here, 1. Alright, at the boundaries themselves, each of these would be closed. So I would have a closed circle at 1, closed circle, right, because of these equal signs. And then in between would be shaded because it's everything between negative 5 and 1 that forms a part of the solution. Alright, of course, writing my answer set builder notation, my solution set is exactly what I had solved there. Minus 5 less than or equal to x less than or equal to 1. Okay. If you wish, we could do a little aside here, and I want to keep everything on. If I test, a convenient point to test is, say, x equals 0. If I put that in my original inequality, I end up with negative 7, the 2 times 0 would go away, 3 less than or equal to 5. When I look at this, and if I cover a portion, so if I were to, let's do this. So if I were to cover this portion, and I looked at it, I would have negative 3 is less than or equal to 3, which is a true statement. Alright, however, if I now cover this part, I would see that 3 is less than or equal to 5 is also a true statement. Hence, the entire thing is true. So I know that I have shaded the correct region based on this idea of taking a test value in the interval that you have solved for and checking the solution. Let's do a few more with this combined inequalities and see what we end up with. Okay. Yes, this inequality is a closed interval because of the 2 endpoints being closed. Let's make it look a little bit scarier. Right, so it's better to make it look scary now than when you get into some sort of test or quiz. Alright, again, the key idea, I wanted to simplify or get rid of the denominator that's here. Right? So think about it this way, that this was missing. What would you have done if you only had the other part? You would say, let's multiply both sides by positive 2. So it's the same idea. Let's look at the full thing all at once. And we're using the idea multiply by 2. Sorry, multiply by 2. Okay. So if I do that, this would be 2 times 2 times Okay. All right, what do I get now? If I multiply, I would end up with 2. Here in the middle term, these would cancel. I just end up with x minus 1. And in the last term, 2 times 3 is 6. So that was relatively easy. The next step is that I want to get rid of the minus 1. The opposite of minus 1 is adding 1 to each part. So if I do that, I would have plus 1, plus 1, plus 1. And let's see what we have. Let's just write in. Okay, so combining 3 is less than or equal to x is less than 7. Let's graph. My graph would be, let's put 0 here. Okay, so I am going to be using, this is 3, this is 7. Okay. What do I want? Alright, so on the boundary that has 3, it will be a closed circle. 7 will be an open circle, and then in between I have a shaded region. Okay, and my solution set is exactly that, x such that 3 is less than or equal to x is less than 7. Again, remember when you have this, it is really just an and statement, but a bit more convenient sometimes for us to look at things in this manner. Alright, let's do one more where I want to change things up. Well, a couple more, 2 more at least, where I want to change things up. Alright, so this time solve the set. So I'm going to be a bit more formal about it this time. Minus 6 is less than or equal to 4 minus 2m, which is less than 8. And m is a member of z. See what you remember. Okay, so as usual, we will take this inequality out. And first thing, isolate the term with the variable. So we want to leave the minus 2 in there. I'm going to simplify my life a bit rather than writing everything throughout. I'm going to subtract 4 from all the parts. So we ended up negative 10 minus 2m and 4. Now I want to divide by negative 2, but remember you have to reverse the inequality. Okay. So as usual, when I do this, I'm not going to reverse the inequality. I'm going to indicate that I am going to do that in a step shortly. 4 over negative 2. And now let's simplify and actually reverse these things. So we have 5 is greater than or equal to m, which is greater than negative 2. Now, we don't like this form of the inequality. 5, yes, is greater than negative 2. So again, if I look at this, oops, I'll change the color here. So if I got rid of one part, we can always say that 5 is greater than or equal to negative 2. That's the true statement. But we hate writing things in the opposite way than they would appear on a number line. So let's go back and rewrite this item. Okay. Now recall when I had something before, if I had A is less than B and I changed the sides, we would change the order. We would change the sides, switch the sides, we change the inequality. So in the same way, I'm going to do that. So -2, M wouldn't change, right? So I'm really switching the left and right side, and we would end up with this. So it's literally reading from the left, or reading rather from the right, but writing it as we go down. All right, now look carefully. If some of you went and automatically did this, where you put in, say, -2 is here, 0, 2, 4, 6, so 5 would be here. If you went in and did this, open, and since I used the wrong color, you would be incorrect. All right, why? Because, all right, so let's even take that out. You'd be incorrect because we are not dealing with the real numbers, we are dealing with the integers. Whoops. So integers. What happens with the integers, or what are the integers? Integers were the whole numbers and their additive opposites. So what we would actually have to do to plot this, even if I am claiming and putting it on a number line, is to definitely put in the numbers here and say, okay, these are the solutions. 1, 2, 3, 4. And in fact, I really need to get rid of, there should be no open circle. If my solution is the integers. So let's see if I can get rid of that without now erasing the entire thing. Maybe I can. There. So since my set is just the integers, I can actually write my solution as just -1, 0, 1, 2, 3, 4, and 5. Okay. So be careful when we do put in a number system that we want you to work with. Okay. All right. Okay. So practice some more from the workbooks, and we will continue next time. Do review everything about solving equations, solving inequality, combine inequalities, because we're moving on to absolute value equations and inequalities. And yeah, I think that's the absolute value equations, or absolute value is the same thing as modulus. This is what you've been doing before from previous classes. If you haven't done it, then you'll be introduced to what we're about to do. Look at one more where it's not as straightforward as what we had in these previous combined statement, particularly in this fashion. Right, in here I just want to point out with, say, number 9, number 10, we had only one variable, which was at the center, numbers on either end. Here in number 10, the same situation, one place with a variable, the numbers on the ends of this inequality. All right. Now let's look at a situation, and we'll only do one because there'll be enough practice in your workbook on this, and let's make it a little bit interesting. And we're going to talk about some possibilities, but it will be easiest, as we will see, to go through and actually divide up this inequality into its two parts. All right, here we can see that there are x's in every portion, so all three portions. If I said, okay, let me even try to subtract x from all the parts, I still won't end up getting just numbers on the ends. So that method will not be useful here. Right. So what we'll have to do is we'll have to call back on our knowledge of this, and let's just recall something here. When we had A is less than B is less than C, I want you to remember that this can be written as A is less than B and B is less than C. If you further need to change the order of that part, that's fine, but I don't really care about doing that right now. I just want to get to the nitty-gritty of the meaning of this combined inequality in line 1 and separating it in its two parts. Okay? So let's do that here. So we would have x minus 5 is less than or equal to 3x minus 5. And the key word, do not just, let me write this correctly first and then say something. Some of you have the habit of writing two pieces or an inequality, two inequalities, and there is no word to join them together. You will have points penalized from your work if you do that. You must from the beginning indicate what the words are that you are using, whether it's an and or an or. Without that, you will really take off some points. If this is can't highlight it enough, I need the word there that you are going to be using. Alright, so let's go through the process of simplifying each part of this, or each of the inequalities that we have. And I'll give you a moment to go ahead and do that. Alright, so, okay. Alright, so let me just do it this way, minus 5 plus 5. I'm going to be dividing by negative 2 here. So it means I reverse the inequality. Doesn't matter if I write 0 divided by negative 2, it will still be 0. X is greater than or equal to 0. I can do the other side, 3x minus 2x, and 2 plus 5, that's 7. And what else do we have? We have just x. So we end up, let me just be good about it, we end up with these two inequalities. Alright, and if we look at this on the number lines, let's do it here. After a while, some of you will be able to do this in one go on a number line. You won't have to do the various portions. X is less than 7. I put 0 down here. And 7 is about there. I'll put it on all of them. Alright, so we would have these three number lines, and let's complete the first two. Close circle at 0 and open circle there. Let's shade the regions. Everything to the right. Trust that you have finished yours and are now checking what you get. We would see that we have the three regions. Again, it would be a bounded interval. Region 2 is what we're going to be getting, and we'll have to look at boundaries. The 0 will be included because it's included in both sets, so yes, and implied that it's there too. It's not no for 7. It's not present in 1, so it can't be present in the final solution. So we have a half open interval, and the solution, our final solution set, would be the set of x's such that write it in the order that it appears on the number line. 0 is less than or equal to x is less than 7. Okay.